In this video, I'm going to go through the remaining two rules here in 7.3, namely De Morgan's and then distribution. These rules are slightly trickier than our previous three rules, com, associativity, and double negation. While I'm explaining De Morgan's as well as distribution, I'll also give you a quick explanation as to why these rules of replacement actually work by relating it back to chapter number 6 in our truth tables. And this explanation will also work for the rules which will be introduced in 7.4, 5 more rules of replacement that we'll learn about involving the horseshoes and the triple bars in 7.4. So let's start here with our first rule finally, rule number 9 as it's labeled in the text, namely De Morgan's, just simply abbreviated DM. So De Morgan's really, to pull it off, involves two separate steps. First of all, you'll notice that De Morgan's, as is the case for almost all of these rules here in 7.3, deals only with dots and wedges. So once again, can't use De Morgan's if it involves a horseshoe or a triple bar. The two steps to pull off De Morgan's are as follows. And it depends here on the direction that we happen to be going, if we're going from right to left or left to right. But the most common application of De Morgan's is to distribute the tilde. If you recall from chapter number 6, I told you never ever distribute the tilde when it's on the outside of the parentheses, at least not until I tell you to. So finally we're to the point in the chapter, the point in the text, where it is appropriate to distribute the tilde when it's on the outside of the parentheses. So let's suppose, finally getting to an example here, let's suppose that we had something like this. Not parentheses, A or B. This is a prime candidate for De Morgan's, and the first step is to distribute that tilde. And when I say distribute, I mean apply it to the variables on the inside of the parentheses. So apply the tilde to the A, and also apply it to the B. So that's the first step, distribute the tilde, not A, not B. And the second step here is to flip the operator. Just speaking loosely here, flip the operator. We started with a wedge, so we'll flip that. We'll flip that to a dot. If we had started with a dot, we would switch it to a wedge. Again, these rules only deal with dots and wedges. So if you start with a wedge, flip it to a dot. If you start with a dot, flip it to a wedge. And those are the two basic steps to pull off De Morgan's. Distribute the tilde on the outside of the parentheses, meaning apply it to the variables on the inside. In this case, apply it to the A and to the B, and then flip the operator. Start with a wedge, flip it to a dot. If we had started up here with a dot, you would flip it to a wedge. As is the case for all of these rules, as indicated again by the 4 dots, De Morgan's too can go both directions. We can either distribute the tilde when it's on the outside of the parentheses, or if we start with line number 2, we can, so to speak, to put it crudely, suck out that tilde. We can bump the tilde away from the A and the B respectively, moving it to the outside of the parentheses. We started with a dot as the operator. We would flip that to a wedge, and then just leaving A and B respectively on the inside. So again, De Morgan's can go either of two directions. We can either distribute the tilde, or we can, to put it again crudely, suck out that tilde. But those are the two basic ways to pull off De Morgan's. As is the case again for all of these rules, De Morgan's can be done to one side or the other. So let's suppose that we started with, say, A, triple bar, not B or D. We could, if we needed to, do De Morgan's just simply to the right side, leaving the A and the triple bar exactly as they presently stand. So we would get A triple bar, distribute the tilde, apply it to the B and the D respectively. Not B, not D, we started with a wedge, flip that to a dot, put in our parentheses to clearly identify this triple bar still as the main logical operator, and that would be De Morgan's as applied here, we'll say, to line 1. 1 De Morgan's, and that would be our justification. So let me quickly, before I move on to our last rule, distribution, explain to you why De Morgan's works. The explanation is a little bit different than the explanation for our rules of inference. Improving our rules of inference and demonstrating that they work, we tested, using our truth tables, we tested for validity. Here, we can demonstrate that the rules of inference are logically equivalent statements. Essentially what we're doing is saying that the statement on the left-hand side is logically equivalent to the statement on the right-hand side of the 4 dots, that is. And vice versa, of course, again indicating that's a two-way street. So let me start here with the visual explanation of rule number 9, De Morgan's, as given to us in the text. The visual explanation is not parentheses P and Q. We see our 4 dots, I'll leave that out. Not P or not Q here in parentheses. So we're again exchanging this statement for that statement, or replacing this statement with that statement, or vice versa, replacing this statement with that statement. Thus, they're called the rules of replacement. Why does this work? Well, again, because the statements are said to be logically equivalent, which I'll now prove via a truth table. So let's construct our truth table here for the 2 separate statements, kind of the number of unique variables. There are 2, we've got P's and Q's. So that tells us, as you already know, that there are 4 lines in this truth table. I'll start on the far left-hand side, defining P as T, T, F, F. Once I've defined a variable, define it in the exact same way, even though the second appearance of P now is in the second statement. The second appearance of P is negated, so I'll reverse this ordering, thereby taking care of the tilde immediately. F, F, T, T. And now that just leaves us with the Q to define. So instead of T, T, F, F, I'll alternate all the way down, T, F, T, F, filling up our 4 lines. The second appearance of Q is negated, so I'll flip that, F, T, F, T. And now we just need to simply solve for the remaining operators, 1 statement at a time. For no particular reason, I'll start on the left and then finish up the statement on the far right. So T and T, that's true, negate it, that becomes false. T and F, that's false, negate it, that becomes true. And the same for these last 2 lines here. It starts out F, and then we negate it, and it's true. Circle the column under the main logical operator, in this case the tilde. And that completes our first statement. To take care of the second statement, we just have the wedge to deal with. F wedge F, that's our special case, that's false. F wedge T, that would be true. And the last 2 lines here also turn out to be true. Circle the column underneath the main logical operator. And now let's compare the lines one at a time. Where this one's false, this one turns out to be false. And where the first statement turns out to be true, the last 3 lines, this one also turns out to be true. So therefore, if you recall back to chapter number 6, we've proved that these 2 statements are logically equivalent. And that's why these rules of inference work. We can replace this statement with this statement, or vice versa, because again, they're logically equivalent, meaning that they yield the same truth value in all possible worlds under all logically possible combinations for P and Q respectively. So that's, again, why these rules work. So now that